So, in cryptography, we can basically characterize a cryptographic system in three ways. So, we can characterize a cryptographic system by the type of encryption operations used. That is the first thing. So, when we try to characterize cryptography in terms of the type of encryption operation used, we're basically saying they are what we call substitution techniques, transposition techniques, as well as the product. Then, you can also decide to characterize cryptography using the number of keys used. So we're basically saying we have two types of keys. It can either be private or public, or it can either be a single key or a two key. But most people often use the word private and public key. Also, we can also characterize the cryptographic system in terms of way in which the plain text is processed. So you will discover that there are some encryption algorithms that process the plain text as a block. Then there are also some algorithms that process the plain text in a stream. So, cryptanalysis, we're basically saying the objective is to recover key, not just the message. So, when a hacker is making use of cryptanalysis, or when he is trying to break the code, the objective is for him to recover the key and not just the message. So, on cryptanalysis, we have what we call general approaches to cryptanalysis. We have what we call a cryptanalytic attack as well as a brute force attack. So, if either of the two succeed, all key use were basically compromised. If a hacker makes use of a cryptanalytic attack, or if he makes use of the brute force attack, but during cryptanalysis, if he or she succeeds, then as an organization we will be compromised. So, on cryptanalytic attacks, we have basically various types of cryptanalytic attacks. The first one is what we call ciphertext only. So, as the word simply means, is we're basically saying on the ciphertext only, we only know the algorithm and the ciphertext. And this type of attack is statistical, or we know or can only identify the plain text. Then we have what we call the non-plain text. We know or we suspect the plain text and the ciphertext. We have what we call a chosen plain text. On a chosen plain text, we're simply saying we select the plain text and obtain the ciphertext. We have what we call a chosen ciphertext. We basically select the ciphertext and obtain a plain text. We also have what we call a chosen text. A chosen text simply means we select a plain text or a ciphertext to either encrypt or to decrypt. So, we have what we call a ciphertext only. On ciphertext only, we are simply saying we only know the algorithm and ciphertext. And we're also saying it is statistical. So we're basically saying you can either know or can also identify the plain text. Then on non-plain text, we're simply saying we know or suspect the plain text and ciphertext. Then, as a cryptanalytic attack, we also have chosen plain text. On chosen plain text, we are simply saying you select the plain text and obtain the ciphertext. We also have what we call chosen ciphertext. So on chosen ciphertext, we are simply saying select the ciphertext and obtain plain text. Then chosen text. Chosen text simply means select plain text or ciphertext to encrypt or decrypt. So these types of cryptanalytic attacks can be diagrammatically represented as follows. On ciphertext only attack, we're basically saying we have Bob and Eve who are simply we have Bob and Alice who are simply trying to convey a message. But at the middle we have Eve. So we're basically saying a plain text is converted using an encryption algorithm to a ciphertext. Then that ciphertext is then decrypted by Alice. But before that ciphertext is decrypted by Alice, we have someone who intercepts known as Eve. So Eve knows the encryption algorithm and tries to intercept the message using the key. That's on the ciphertext only attack. Then on the non-plain text attack, we're simply saying Eve knows the plain text and Eve also knows the ciphertext. Chosen plain text, we're basically saying when Bob is simply trying to send a message to Alice, what does Eve know? Eve actually knows the plain text that has been chosen by Bob, as well as the ciphertext. So you will discover that most of these cryptanalytic attacks can also be or explained diagrammatically as what is being or as what is on the PPT. So we also have what we call unconditional security. So on unconditional security, we're simply saying no matter how much computer power or time that you have, the cipher cannot be broken, since the ciphertext provides insufficient information to uniquely determine the corresponding plaintext. But on computational security, we are basically saying, given limited computing resources, for example, the time that you need to actually calculate, the time needed for calculation is greater than the edge of the universe. We simply say, which we're simply trying to say that the cipher cannot be broken. If you remember quite well, we said during cryptanalysis, you can either use a cryptanalytic attack or a brute force attack. So now we're going to be discussing with respect to what a brute force attack is. So a brute force attack, in simpler terms, we're simply trying to try any possible key that we can actually think of. Brute force is actually equated to guessing. So we're basically saying we're making use of it's always possible to simply try every key. So we're basically saying it is the most basic attack and is proportional to the key size. We assume either we know or we recognize a plain text. That's why I said the brute force attack, you'll be trying to guess possible plain text that you think might work for you. So below is a table that has the key size in bits, number of alternative keys, time required at decryption, as well as time required at decryption in at 1. So that's what that table is simply trying to illustrate. Now, on classic encryption techniques, we mentioned that we have symmetric encryption. We have the symmetric cipher model, right? We also mentioned that we have substitution techniques. We also mentioned that we have transposition techniques, as well as steganography. So now we have been discussing with respect to symmetric cipher model. So now we're going to jump into substitution techniques. So on substitution techniques, we're simply saying where letters of plain text are replaced by other letters, or by numbers or symbols, or if a plain text is viewed as a sequence of bits, then substitution involves replacing plain text bit patterns with ciphertext bit patterns. So the most earliest or the first substitution technique that has been used, or that was developed initially, is what we call the Caesar cipher. So the Caesar cipher is known as the earliest known substitution cipher. Why was it named Caesar cipher? It was named after Julius Caesar. So this Caesar cipher first attested use by the military. They were basically saying, how does it work? It replaces each letter by a third letter on. Example, we have a plain text known as "Meet me after the toga party." So if we try and convert that plain text using the Caesar cipher, we have PHHW, PHDIW, HU, WKH, WRJD, SDU, WB. So we're basically saying the Caesar cipher looks at each and every letter on the plain text that we have on the plain text, and it substitutes that letter or each letter with the third letter on the alphabet. So for instance, M using Caesar cipher is converted to P. E using Caesar cipher is converted into H. So you're simply saying M, N, O, P. So with Caesar cipher, you start by reading the next letter, which is from N, we have N, then we have O, so the third letter becomes P. So we're basically saying P substitutes the letter M, since it is the third letter that you actually obtain in the alphabet from M. So Caesar cipher is actually very, very easy to understand. Then we also have what we call a monoalphabetic cipher. So now the monoalphabetic cipher, rather than just shifting the alphabet, it could shuffle, jumble the letters. So we're basically saying each plain text letter maps to a different random ciphertext letter. Hence we're basically saying the key is 26 letters long. That's the monoalphabetic cipher. So, on the monoalphabetic cipher security, we're simply saying now we have a total of 26 factorial, which is about 4 times 10 to the power 26 keys. With so many keys, you might actually think it is secure, but will be wrong. Problem is the language characteristics. Then, on the substitution techniques, we have what we call the play-fair cipher. So, not even the large numbers of keys in the monoalphabetic cipher provide security. One approach to improving security was to encrypt multiple letters. So, the play-fair cipher is an example. The play-fair cipher was invented by Charles Wheatstone in 1854, but named after his friend Byron Playfair. How wonderful is that? I believe you are such a good friend. So, the Playfair cipher makes use of a Playfair key matrix, which is usually a 5x5 matrix of letters based on keywords. So, first of all, we fill in the letters of the keyword. Then, fill the rest of the matrix with other letters. So, using a keyword, let's say for instance, monarchy. On the 5x5, we first of all fill in the keyword, which is monarch. Then you look at the keyword, then you start looking at the words that are not in the keyword. Let's say for instance, on the keyword we have an A on the letters of the alphabet. So you don't necessarily have to write the A. You then look at the next word, which is B. If you have a keyword B on the if you have the letter B on the keyword, you jump on to the next. So basically that's what you use to actually substitute in the 5x5 matrix. But now the letters I and J, if you have the letters I and J are usually written in the same box of the matrix, I or J. So if you also have basically what we're simply trying to say is when encrypting and decrypting, plain text is encrypted 2 letters at a time. If a pair is repeated letter, you insert a file like X. If both letters fall in the same row, you replace each with the letter to the right. That is wrapping back to start from the end. If both letters fall in the same column, you replace each with the letter below, that is wrapping to top from bottom. Otherwise, each letter is replaced by the letter in the same row and in the same column of the other letter or the other pair. So, unlike the monoalphabetic cipher, there has been some security enhancement on the Playfair cipher, whereby we're saying since we have 26 by 26, which means we have 676 diagrams, and would need a 676 entry frequency table to analyze versus the 26 for the monoalphabetic cipher. And correspondingly, more ciphertext is used. They were basically saying this Playfair cipher was widely used for many years, for example by the US and British military in the World War I. The Playfair cipher, it can be broken and given a few hundreds letters, since still has much of plain text structure. So we also have what we call the polyalphabetic ciphers. So the polyalphabetic substitution cipher, it improves security using multiple cipher alphabets. So This, however, makes cryptanalysis harder, with more alphabets to guess and flatter frequency distribution. So polyalphabetic ciphers use a key to select which alphabet is used for each letter of the message, and uses each alphabet in turn. And it also repeats from start after end of the key is reached. We have what we call the Wegener cipher. So the Wegener cipher is a method of encrypting alphabetic text by using a series of different Caesar cipher based on the letters of a keyword. It is a simple form of polyalphabetic substitution. So the Wegener cipher is named for Blaise de Wegener. Although Giovanni Battista Belliso had invented the cipher earlier, Wegener did invent a stronger auto-key cipher. We also have what we call the Kasiski method. So, this method was developed by Babbage or Kasiski. We're basically saying their repetitions in the ciphertext gives clues to period. So find the same plain text and exact period apart, which results in the same ciphertext. Of course, could also be a random fluke. For example, it suggests the size of 3 or 9, then attack each monoalphabetic cipher individually using the same technique as before. So we also have what we call the auto-key cipher. So on the auto-key cipher, ideally we want a key as long as the message. So Wegener proposed the auto-key cipher, with the keyword is prefixed to a message as the key. How interesting is that? So knowing the keyword can recover the first few letters. So we basically use this in turn on the rest of the message, but still have frequency characteristics to attack. For example, given the key deceptive, we are discovered as the key, the plain text will be, we are discovered, save yourself. We also have another substitution technique known as the Venom cipher. So, this Venom cipher, its ultimate defense is to use a key as long as the plain text, with no statistical relationship to it. This Venom cipher was invented by AT&T engineer Gilbert Venom in 1918. So it was originally proposed using a very long but eventually repeating key. So on one time pad we're simply saying if a truly random key, as long as the message is used, the cipher will be secure. It is called a one-time pad. It is unbreakable since we are saying ciphertext bears no statistical relationship to the plain text. Since for any plain text and any ciphertext there exists a key mapping one to another, can only use the key once though. Problem is in generation and safe distribution of the